new will make us proud. And to try something new, you need to try new things and not be afraid to be wrong, said Roy T. Bennett. Today, on this auspicious day, we have gathered here to explore and learn something new on the topic, the random processes. And that will be helpful for the better understanding of concepts of random processes. Welcome, your smiles, and joy wants on welcome. I am glad to respectfully and cordially welcome the chief guest of this evening, Dr.K.Subathra ma'am, Professor, Department of Maths, Sri Sairam Engineering College, Chennai. Welcome, ma'am. Next, I express my warm welcome to our esteemed principal and vice principal to this webinar. You have always been our greatest backbone and constantly encouraging our efforts. Welcome, sir. Next, I would like to welcome Dr. S. Chitra, Head of the Department of Maths, SRMVEC Engineering College. Welcome, ma'am. Next, I extend my warm welcome to the beloved teachers who assist us in not just our development, but also enhancing our creativity and knowledge. Welcome, teachers. Last but not the least, I extend my joyous welcome to the energetic students who always wanted to excel in their life. Welcome you all, students. Once again, I welcome everyone who are the part and parcel of this event. I now request all the students to turn on your cameras.
Good evening all. On behalf of Mathematics Association Euler.com, I extend my warm welcome to Dr. Subathra ma'am, Sairam Engineering College, Professor, Department of Mathematics, and I extend my warm welcome to all the teachers of Vijayalakshmi Engineering College and Sairam Engineering College, and all the students of Computer Science Engineering, Cyber Security, and Information Technology students. Thank you.
Thank you, ma'am. Now, it's time to introduce the guest of this evening, Dr. K.Subathra ma'am, Professor, Department of Maths, Sri Sairam Engineering College, Chennai. I request Sundarakannan sir, Assistant Professor, Department of Maths, SRMVEC Engineering College, to give the introduction to the chief guest.
Good evening, one and all. I am very happy to introduce our chief guest, Dr. K.Subathra ma'am, Professor, Sairam Engineering College, Chennai. Her qualification is MSc MPhil Mathematics. She completed her PhD in the complex analysis topic. She has more than 26 years of the teaching experience. She acted as the resource person for the bridge course conducted by Anna University, Chennai. She is the resource person in Decennial EGMA program conducted by the Madras Christian College, Chennai. She was a session chair in the national conferences on recent trends in computer science and mathematics organized by the School of Computer Information and Mathematical Sciences. She was a captain of the math club in Sairam Engineering College. She published various research papers and articles in national and international level. And also she attended the various conferences and he conducted the various conferences and all the events, those who are events has been conducted in Sairam Engineering College. She is a very important person. And finally, currently she is working in a topic of mathematics and the machine learning process. I welcome the ma'am to deliver this acceptance. First of all, I just thanked Dr. K.Subathra ma'am to acceptance our request, and the session is yours. Thank you, ma'am. Thank you, students. The students, please, on your video, please, only students. Staffs need not to be open. All the students, please be open your videos. Ma'am, Subhatra ma'am, please.
Thank you, sir.
The session is
Thank
yours.
You for your
Thank
wonderful welcome address, sir.
Thank you, ma'am.
I'm very grateful to you, Chitra, Sundarakannan, sir. First of all, I would express my sincere thanks to good evening, all of us. I would express my sincere thanks to the management, SRM institutions, the principal, SRMVEC Engineering College, Vice Principal of SRMVEC Engineering College, Chitra Madam, Head of the Department of Valley Engineering College, and the organizer of this webinar, Sundarakannan sir, Vasiki Madam, and Vijayalakshmi Madam, and the faculty members of SR Engineering College for giving me this opportunity to deliver a lecture on random process to SRM Engineering College students. Thank you very much for this wonderful opportunity. I'll share my screen now, sir. Actually, sir, is my screen visible?
Yes, ma'am. Yeah, visible.
Actually, today's topic is random process. Before going to random process, first of all, we should know what is random variable. See the coin. When you're flipping the coin, you will get either head or tail. Head is denoted by H, tail is denoted by T. Actually, these two are alphabets, head and tail. H and T are alphabets. But to take a die, when you're throwing this die, you will get numbers 1, 1 to 6. That is either you get number 1 or 2 or 3, 4 or 5 or 6. What is the difference between these two? The outcome of the coin is a non-numerical value. It is an alphabet. But when you are throwing a die, you are getting only alphabets. If the outcome is a non-numerical value, that is alphabet, it is very difficult to calculate the statistical properties like mean, variance, and so on. So it is necessary to convert the alphabets into not numerical values, that is non-numerical values to numerical values. That's why we have random variable. So random variable is a function that assigns numerical values to non-numerical outcomes. So it's a function or rule that assigns numerical values to non-numerical outcomes. Then only we can calculate our statistical constants. Okay. So first, assign numerical values to non-numerical outcomes. So in the coin toss problems, you have to assign 1 as 1 for head and 0 for tail. Or you can assign 0 for head or 1 for tail. Okay. So now onwards, when you are tossing a coin, your outcomes are not head and tail. The outcomes are only 1 or 0. Random variables are usually denoted by the alphabets like capital letters X and Y. Here you take the random variable as X, the capital letter X. Okay, there are two types of random variables now. One is discrete random variable, other one is continuous random variable. Discrete random variable means the random variable is, now we are denoting the random variable as X. The random variable capital X takes finite number or countably infinite number of values. See this picture, it is an apartment. In this apartment, you have number of houses. You can count how many houses in this apartment. It's a finite quantity. So this is coming under discrete random variable. See my next picture. This is number of peoples of India. You can take the number of people of India or number of peoples of globe. You can count. See this numbers coming in rows. Okay, so you can count it. This is an infinite number. Some 300 or 400 rows are coming. Okay, so discrete random variable is a finite number or countably infinite number of values. It is a countable number, takes infinite number of values. So these examples are coming under discrete random variable. The number of houses in an apartment, number of people in the globe. Next is continuous random variable. See the picture first. Actually, continuous random variable takes all values in an interval. See the picture. It's a classroom. Suppose I want to find out the average height of the students in the classroom. It's not necessary to take the height of all students of the class. Okay, you can take a random sample of or 10 or 15 students and generalize that height. Suppose this is a class consisting of 60 students. This is a primary school. So their height lies between 70 centimeter to some 100 centimeter. Okay. So their height cannot go beyond that 100 centimeter, or it will not come down below 70. So their height range between 70 to 100. Okay. 1 second. Sorry. So their heights lies between 70 to 100 only. So among the 60 students, their height ranges from 70 to 100. Take my next picture. This is a cluster of oranges. In this cluster, 2 oranges are tasty. That means the sugar content in that oranges are very high. Some oranges are medium in taste. That means the sugar content in that oranges are medium. Okay. Some oranges are sour in taste. That means that oranges doesn't have any sugar content. That is, sugar content in that oranges are nil. Okay. So sugar content in this oranges lies between 0% to 50% or some 10% to 70%. So sugar content ranges between 10% to some 60%. That is lies between 10 to 60 or 10 to 60. So these examples are coming under continuous random variabilities. Okay, next random process. Now we know what is random variable. If you are associating a time function together with the random variable, you are getting random process. So random process is a collection of random variables together with time function. In random variables, you have only sample space, but in random process, you have time function also. Okay. This random process can be classified into four, sorry, missed example. Random, you take this picture. This is a share market. You can see this board in share market. You take a day's trading in a share market. Okay. Example, say trading is between 10 a.m. to evening 5 p.m. You take a company share at 10 a.m. For that particular company, I am fixing the share price as 300. As time increases, the share prices will go up sometimes, or sometimes it will go down. That is, sometimes the 300 rupees reaches 400 rupees. Sometimes it's coming down to 200 or 250 rupees. Okay, so that quantity is the discrete value, but time range from 10 a.m. to evening 5 p.m. So this process coming under your random process. Next one is amplitude of a signal. If the signal is of pure signal, then your amplitude is high. If the signal is contaminated or noise is more, then your amplitude is very low. Okay, so depending upon the time, the amplitude is not stable, amplitude goes up and down, depending upon the nature of the signal. If the noise increases, amplitude will come down. If the signal has less noise, it is medium amplitude. If there is no noise, the amplitude is high. So these are examples of random process. There are, depending upon the nature of S and T, you can classify the random process into 4 types. One is discrete random sequence, continuous random sequence, discrete random process, and continuous random process, depending upon the nature of S and T. You know, S is sample space. That sample space is discrete or continuous. Then depending upon the time function T, if T is discrete, then you can say that is sequence. If T is continuous, you can say that as process. Okay. If S and T are discrete, S is a sample space, T is a time function. If S and T are discrete, then you can call that as discrete random sequence. To take this example, I am repeatedly throwing this die. I am interested only in the fifth toss of a die, this die. So fifth toss is either 1, 2, or 3, so on up to 6. So I am interested only in the fifth toss. The outcome is also discrete. Time is also discrete. Outcome is also discrete. So S and T are discrete. So this is discrete random sequence. Okay. X and represents the outcome of the nth toss of a fair die coin, anything we can take. Second one, S is continuous, T is discrete. I am interested to find out the temperature between 11 a.m. to 12 noon in a particular day. Nowadays, the city is very hot, so the temperature is very high between 11 a.m. to 12 noon. Surya. So I am interested only to find out the temperature in 1 hour. Time period is 11 a.m. to 12 noon. So there, the temperature varies from 30 at 11 a.m. It is, I am fixing the temperature is 30 degrees Celsius. So it goes up to 40 degrees Celsius, or sometimes it is too hot nowadays, it reaches 42 degrees Celsius. So the 11 a.m. it is 30 degrees. 11:15 sometimes it is 35 degrees. Sometimes at is 11:30 it reaches 32 degrees also. Temperature varies from 30 to 40 degrees Celsius or 42 degrees Celsius, but the time is 1 hour. So time is discrete and sample space is continuous. So that's this one is called continuous random sequence. Next one is discrete random process. Okay, take a telephone. Number of telephone calls received in a particular day. In all our phone, we have telephones or mobile phones. Number of calls receiving in a day. Number of calls receiving in an hour. So these are coming under discrete random process. Okay, so their number of calls discrete and timing is between 9 a.m. to 10 a.m. 9 a.m. to 10 p.m. 1 day or 1 hour, 2 hours. Their time is continuous. Number of calls is discrete. So that's what this one is called, discrete random process. Next is continuous random process. You take this example. I take a rice cooker. See, I want to cook rice. Cooking time takes only 20 minutes. That is time ranges between 0 to 20. Okay, I want the rice. Initially, time t equal to 0. The rice is also of temperature 0. As time increases, the temperature of rice also increases from 0 degree Celsius to 100 degrees Celsius only. Okay, boiling temperature of water is 100 degrees Celsius. So yes, S is also continuous. T is also continuous. S also ranges from 0 to 100 degrees Celsius. T also ranges from 0 to 20 minutes. Okay. So here both S and T are continuous. It is continuous random process. Now,
Excuse me, ma'am.
mean of a sir.
Hello. இல்ல எக்கோ இருக்கு மேம், எக்கோ வருது. ஸோ இது டூ டிவைஸ் யூஸ் பண்றீங்களா மேம்?
இல்லையே சார்.
ஏதோ சம்வேர் எக்கோ வருது. இப்போ
1 second சார்.
இப்போ கிளியரா இருக்கு. ஓகே. Fine.
One second, the laptop மட்டும்தான் சார் வச்சிருக்கேன்.
சரிங்க மேம். ஓகே ஓகே. இப்போ கிளீனா இருக்கு. நான் டபுள் வாய்ஸ் அப்படியே எக்கோவா கேட்டுட்டு இருந்தது அதனால. ஓகே மேம். சாரி ஃபார் த டிஸ்டர்பன்ஸ். சாரி மேம்.
இல்ல சார், முதல்ல நீங்க சொல்லிருக்கலாம். ஓகே.
ஓகே மேம். இப்போ கிளீனா இருக்கு மேம். தேங்க் யூ. கண்டினியூ பண்ணுங்க மேம். சாரி.
Okay sir. See, mean. Next is mean of a random process. We all know how to calculate the mean of a random variable. Okay, mean of random variable is either it is if it is a discrete random variable, sigma over x into sigma over x into p of x. If it is a continuous random variable, integral between the limits x into probability density function into dx. Here it is a mean of random process. Same formula with respect to time. There e of x, there we denoted that by mu. Here with respect to time function e of x of t. Here random variable with respect to time is actually random process. Okay, so that we are here we are denoting that by mu x. Mu x means mean with respect to the random variable x. So mu x of t means mean with respect to the random variable x of t. Okay, this mean is times called ensemble averages. Ensemble average is nothing but the mean of the random process x of t. Here of random process is x of t. The mean of random process x of t is called ensemble average and is defined by e of x of t. Okay. In between this random process, you have so many random variables. Okay. Suppose if it is a discrete random variable, it can have n number of random variables. Finding the average of that random variables with the help of this formula, 1 by 2 pi, 1 by 2t into integral minus t2 plus t x of t dt is called the time average. The time function is defined between the interval minus t2 plus t. This is actually the average of the random variable present in the random process. Time averages are not equal to ensemble averages. Ensemble averages are averages of the random process. Time average is the average of the random variable present in the random process. That random variable is also with respect to time function only. So normally time averages are not equal to ensemble averages. This time averages are used to estimate ensemble averages. In some special random process, this time averages are equal to ensemble averages. That random processes are called periodic process. Okay. This is an example. See the picture. Car is running. Okay. To find out the speed of a car, we have to calculate the distance traveled by the car by time. Here, to calculate the speed, we are finding the distance of the car with respect to time. So average with respect to time is an example of this one is actually an example of a mean of a random process. So if the time average is equal to ensemble average, then that process is called periodic process. It is not always a few random. This is equal to 2. Here in our syllabus is periodic process. Now the correlation random process. Correlation relationship. Correlation between x and y means correlation between the random variables x and y. Autocorrelation means finding relationship within the variable. That is correlate variable to its own. So finding relationship within the random variable x of t. Here we have taken the random process x of t. This random process x of t contains a lot of random variables. So finding relationship among itself is actually called autocorrelation. This autocorrelation is denoted by Rx of t. This relationship is we are finding with respect to time function. That time function is t and t plus tau. Here t and t plus tau are two different timings. Tau is the change in time. So we are calculating autocorrelation function of a random process x of t with respect to two time intervals t and t plus tau. It is defined by expected value of x of t into x of t plus tau. So, E of x of t by x of t plus tau is autocorrelation random process x of t. Similarly, autovariance. This is again a statistical property of the random process. It's again finding covariance among the random variables with respect to two time intervals. T1 and T2 is actually autocovariance. We know how we calculate variance in random variables. Their covariance is expected value of x minus mu whole square. X is the random variable, mu is the mean with respect to random variable whole square. That is 2 times you are writing that x minus mu into x minus mu. Here the random process is expected with respect to two timings t1 and t2. So there we are denoting that by x t1 and x of t2. So similar, same formula, but timing is mentioned here. This is x of t1 is the random variable with respect to time t1. Mu x t1 is the mean with respect to time t1. X of t2 is actually the random variable with respect to the time t2. And similarly, mu x of t2 is the mean with respect to the time t2. When you multiply these two and taking expectation, you will get Rx of t1 comma t2 minus product of means with respect to t1 and t2. So autocovariance is nothing. Autocorrelation minus product of means with respect to t1 and t2. Now stationary random process. You take any random process. When you say that random process is stationary, if random process statistical properties, you take any statistical property of the random process. If the statistical properties are invariant, the shift of time origin, then that type of random processes are called stationary random process. Okay, there are two types of random stationary random processes. One is strict sense stationary process, that is triple S process. Other one is WSS process, weak sense stationary process. You take triple S process. A random process is triple SS, that is strict sense stationary or strongly stationary process. If CDF is invariant, CDF means cumulative distribution function is invariant in the time to a shift of time origin. Okay, sorry. CDF is, that is cumulative distribution function is invariant to a shift in the time origin. That is cumulative distribution of the random variable x of t1 is same as cumulative distribution function of the random process x of t1 plus t1 or t plus tau. That tau the change in time. X of t1 is same as x of t1 plus tau, and x of t2 is same as x of t2 plus tau, and so on up to this particular random process has n number of random variables. So that's what I have written up to x of n. Cumulative distribution of this particular random process is invariant under time. Cumulative distribution is invariant under time. Their probability density function is also invariant under time. Probability density function means PDF. PDF is also invariant under time. So that is given here. If the PDF of the variable x is invariant under time, is x of t1 is same as x of t1 plus tau, and x of t2 is same as x of t2 plus tau, and so on up to x of tn is same as x of tn plus tau. Here, t1 and t2 are time functions, and this tau is a time change in time. It is also a positive quantity. If this values are, see for example, if I'm taking n is equal to decade, if I'm I'm taking n is equal to k. That means you have x of t1 is equal to x of t1 plus tau, and x of t2 is equal to x of t2 plus tau, and so on up to x of tk is x of tk plus tau, and not more than that. If these conditions are, that is the joint density function of x of t1 to x of tk is invariant shift of time origin, then that type of random processes are called kth order stationary. Suppose if it is true for n is equal to 1, that is x of t1 is equal to x of t1 plus tau, then that is called first order stationary. If n is equal to 2, that is x of t1, comma x of t2 is same, x of t1 plus tau and x of t2 plus tau. That is n is equal to 2. That case, triplus process is called second order stationary. You take the first order stationary. First order stationary means n is equal to 1. X of t1 is equal to x of t1 plus tau. So that I have taken as this one. That is f of x comma t is equal to f of x comma t plus tau. That is the density function of x of t1. Here t1 is, I have taken t1 as simply t, because we have one time function present there. I have taken t1 as t. When these two are equal only this function independent of time. That means t is not present there. If t is not there means, if you are finding the mean of this function, that means should be a constant. So in a triplus process, first order stationary is the constant. First order stationary is a constant, that is mean of x of t is a constant. When n is equal to 2, you are getting the second order density like this. F of x1 comma x2 and t1 is t1 comma t2, type function is t1 comma t2. That is f of x1 comma x2 because it is second order stationary. So for t1, for the time t1, you have t1 plus tau. For the time function t2, you have t2 plus tau. So f of x1 comma x2 comma t1 comma t2 is same as f of x1 comma x2 comma t1 plus tau comma t2 plus tau. When these two are equal only if left hand side is a function of time difference. This is possible only if the left hand side function is a function of time difference. If this one is a function of time difference, then that one is called autocorrelation. Second order stationary is coming under autocorrelation function. Okay. So this is second order stationary. Second order stationary is denoted by R of t1 comma t2, that you know the value expected that you have already defined what is autocorrelation. There we have defined R of t comma t plus tau was expected value of x of t comma x of t plus tau. Here in case of t, t1, t plus tau, t2. Then White's and state theory. You take any random process, if the mean of the random process is constant, the autocorrelation is the function of time difference, and that type of process are called White's stationary process. You take any stationary process, if the particular process mean is constant and its autocorrelation function is a function of time difference, then that type of processes are called White's stationary process. See, in the previous slide, we have seen strict stationary process properties. There also the mean is constant. Autocorrelation function is a function of time difference. So all plus processes are White's stationary process. Some stationary processes not satisfying the stationary property conditions. So that is that processes are called evolutionary process. So evolutionary processes are not stationary in any sense. That are not stationary. They are different with respect to time origin. That processes are called actually evolutionary process. Power spectral density. Actually, power spectral density is also a statistical property of the random process. Once you know the autocorrelation function, you can easily calculate the power spectral density. Power spectral density is a Fourier transform of the autocorrelation function. We know if the random we have random process, then how we know how you calculate the autocorrelation function of the random process x of t. If you know the spectral density function, suppose if you don't have x of t, you have only spectral density function. In that case, you can calculate the autocorrelation function with the help of Fourier inverse transform. Autocorrelation function of a particular process, if you know the power spectral density, means you simply find the inverse Fourier transform of that function. You will get the autocorrelation of the function. Okay. Then special models of random process. First one is Poisson process. This Poisson process is widely used in models in arrival system. Okay. For example, you take a bus stop. Okay, buses are arriving between 6 morning, 6 a.m. evening, 10 p.m. Every 1 hour, you have assume that every 1 hour you have buses. Uh, Arrival of a particular passenger is not known. Okay, passengers are, passengers are arriving there convenient time. Okay, catch the bus, but their arrival time is not known. It is an unknown quantity. Okay, some passengers will arrive at 30, somebody will arrive at 7 o'clock, and so on. Because you have buses from 6 a.m. To 2 p.m. So their convenient time, they arrive at the bus stop and they'll catch the bus. So arrival time is known, but the average time between arrivals is known in Poisson process. Arrival time, average arrival time between passenger is known in Poisson process. So inter-arrival time is known, but exact time of the passengers is not known. So depending upon their arrival date, you can increase the number of buses. Suppose the passengers are very passengers are rate is very high. Passengers are more in numbers in the bus stand. You can arrange more buses. Okay, suppose arrival rate is very low. That is number of passengers are less. So that case, like you can cancel some buses. Okay, so that is you can apply Poisson process. So there, you know the arrival date. You don't know the exact time of the arrival passenger. So you can model this Poisson process in uh, uh, railway station, railway ticket counters, bus stop ticket counters, telephone offices, then switchboards, then random failure of equipments. You know, the failure of equipments in the time, but duration of time, but the exact time of failure is known. So that cases you can apply Poisson process. The next one is Markov process. The Markov process is actually widely used in all engineering and science and business modeling. This is used to model a system that has less memory in their past. This is used to model that has less memory in their past. Actually, Markov processes are used to find future values. Okay, if you know the present value, it's not necessary to know the past values. So Markov processes are used to find future values that depend on the current value, not on the past value. Depends on the current value, the last immediate value. It is not necessary to the value. See, for example, you all have done your third semester exams. Your final CGP, that is after completion of your 8th semester, your CGPA depends on your 8th semester's performance, not your 12th standard performance or 11th standard performance and so on. So if future value means future GCPA, your degree, okay, your course, depends only on the semester marks that you have got in these semesters, not the past. In that Markov depends only, that is in Markov process interested only in the current value, not on the past values. Okay, so future values depends only on the present value, on the past values. Any take any process, if that process has Markov property, which takes discrete values, whether the time function is discrete or continuous, then that type of process are called Markov chains. You take this one. See, I find out probability of x, but the values of x minus xn minus 2, etc. up to x naught is known. But I want to calculate probability of xn. So that depends only on the present value or the previous value, not on past value. But I know the values from xn minus to x naught. But I'm interested values x naught to xn minus. I am only interested in xn minus because I am in Markov process. So Markov process feature value depends only on present value, not on past values. Okay, so that's what it is given by probability of xn equal to an, given probability of xn equal to an given xn minus 1, xn minus 2, etc. up to x naught. The same as probability of xn equal to an and xn minus an minus 1. Here, see the right hand side value. There, you have probability of xn is equal to an, xn minus 1 is equal to an minus 1. So you are in the state an minus 1 to an, or initially from an minus 1. Now you are to the nth state. Okay. So xn minus 1 to xn, the difference is only 1. So that this is called once transition probability from state a minus 1 to an at the nth step. Nth step means initially you were in probability of x1 is equal to a1 given x naught equal to a naught. To reach probability of xn equal to an given x minus 1 equal to an minus 1, you have taken n steps. That's what this one is called one step transition probability from a n minus 1 to an at the nth step. If the one step probability, this is actually the one step probability because your xn minus 1 state to xn, the difference between n minus 1 and n is 1. That is what it is one step. If one step probability does not depend on the step, if the step does not matter, then that case this Markov chain is actually called homogeneous Markov chain. When the Markov chain is homogeneous, then the one-step probability matrix is denoted by P and J. If I take xn minus 1 ai and xn as aj, then that is denoted by Pij, and the respective matrix is called transition probability matrix. Next one is Gaussian process. Gaussian process used in physical problems, including noise, are well appreciated by special class random process called Gaussian random process. Actually, this is used in communication systems. You take any random process x of t. This x of t is said to be a Gaussian random process. Already I said inside the random process you have so many random variables x of t1, x of t2, etc. x of tn. If this random process x of t is Gaussian, if all these random variables are jointly Gaussian means in one time random you have studied Gaussian distribution. There, the PDF is 1 by sigma root of 2 pi into integral minus infinity to plus infinity e power minus, sorry, by sigma root of 2 pi e power minus of minus whole square divided by 2 sigma square. Here, you are finding the joint PDF of all these uh, random variables. That is actually called Gaussian random process. This Gaussian random process are used in communication systems. Noise in communication system is usually modeled as a Gaussian process. Okay. Usually, when you are transmitting signals channels, most of the times the signals are contaminated. Okay. So that is actually called noise. Noise in communication system is usually modeled as a communication process. Similarly, noise voltages in resistors are called as Gaussian process. Nowadays, actually, this joint PDF of this random variables are actually called multivariate random variables. These variables are actually multivariate random variables are very useful. That is actually machine learning techniques. This multiple variables are very useful in machine learning techniques. Machine learning technique people are using this multivariate techniques in their problems. Okay, that's all my presentation. Thank you for patiently listening. Thank you.
That was an amazing presentation, ma'am. We learned a lot about the random processes. Thank you so much, ma'am. Students can raise your questions now.
Okay, no questions. Okay, thank you, ma'am. Thank you so much. So, next we move to the next session. Next, proceed, Pranava.
No duty is more urgent than that of returning thanks. I now request Vasaki ma'am, Assistant Professor, Department of Maths, SRMVEC Engineering College, to render the oath of thanks.
Good evening to all. On behalf of our department, I take this opportunity to propose vote of thanks on this special occasion. First, I must thank our chief guest, Professor Dr.K.Subathra, Department of Mathematics, Sri Sairam Engineering College, Chennai, for accepting our invitation and also for her wonderful lecture about random processes, starting from the basic concepts. The lecture was really informative. Thank you, ma'am. I express my sincere gratitude to the management for providing the opportunity to organize this lecture. We offer our sincere thanks to our principal sir and vice principal sir for permitting us to conduct this special lecture. I would like to thank our head of the department, Madam Dr. S. Chitra, for her encouragement and moral support for organizing this lecture. I would like to thank our department Mathematics Club Association coordinator, Madam Dr. V. Vijayalakshmi, for her guidance to organize this lecture. I especially thank the event coordinator, Mr. N. Sundarakannan, for his continuous effort to make this lecture as a successful one. I thank our department faculty members for their kind support in organizing this lecture. I thank our student, Ms. Muttukruba of second year Computer Science and Engineering, for her perfect comparing throughout this program. Next, I must thank our beloved students of second year Computer Science and Engineering, Cyber Security, and Electronics and Communication Engineering for their patience, listening, and learning. So once again, I thank you all.
Thank you, ma'am.
Thank you so much, ma'am.